Hi, everyone. Thank you for joining us today for today's PCI-SIG webinar, celebrating 20 years of the PCI Express specification. I'll take a moment to introduce our panelists for today. Our moderator today is Mihaela Erler, Industry Enabling Manager at Intel and also PCI-SIG Marketing Workgroup Chair. We also have Devendra Das Sharma, Senior Fellow and Co-GM of Memory and I/O Technologies and Data Platforms and AI Group at Intel. Also PCI-SIG Board of Directors. We have David Harriman, Distinguished Architect from Ampere Computing, also PCI-SIG Protocol Workgroup Chair and Automotive Workgroup Co-Chair. Also, part of our panel today, we have Manisha Nalanj, I/O Architect and Analog Engineering Manager from Intel, as well as PCI-SIG Electromechanical Mini SFF Connector Workgroup Co-Chair and Compliance Co-Chair. And also today, we have Richard Solomon, who's Technical Marketing Manager for PCIe Controller IP at Synopsys, and PCI-SIG Vice President and Compliance Co-Chair. Now, I'm going to go ahead and hand it over to Devendra to kick things off today.
Greetings, everybody. Thank you for joining us. It's an honor and privilege to do this webinar. PCI-SIG is an open industry consortium with more than 975 member companies worldwide. We have 9 directors in the board. We get elected every year by the members. The current set of board members are shown on this slide. PCI-SIG was established in 1992. PCI-SIG stands for Peripheral Components Interconnects Special Interest Group. And PCI-SIG is responsible for defining the specifications and mechanisms to support the compliance and interoperability of PCI Express technology, and of course, PCI before that. So in a way, PCI-SIG drives the technology from the proverbial cradle to grave. Now let me give a little bit of background on the evolution of PCI Express. PCI Express debuted with the release of PCI Express 1.0 specification in 2003. We double the data rate every generation, as you can see in the table, and we do that while maintaining full backwards compatibility. So for PCIe 1.0 and 2.0, we used 8B, 10B encoding at 2.5 gigatransfers per second and 5 gigatransfers per second, respectively. The interesting thing happened with PCI Express 3.0. We moved to 8 gigatransfers per second instead of going to 10 gigatransfers per second, because our analysis showed that the 10 gigatransfers per second was not feasible within the cost, volumetric, and power constraint based on the types of materials that were available at that time. And we thought our analysis showed that 8 gigatransfers per second was the sweet spot. So in order to double the data rate, we made the change in the encoding scheme from 8B, 10B encoding to 128B, 130B encoding. And we continued with that encoding mechanism for PCIe 4.0 at 16 gigatransfers per second and PCIe 5.0 at 32 gigatransfers per second. For 6.0 specification, we adopted PAM4 signaling at 64 gigatransfers per second, while maintaining the same channel reach and of course with full backwards compatibility with the prior generations. We changed to the flit mode, and we will preserve the same flit mode with PCIe 7.0 at 128 gigatransfers per second. So we have been evolving this technology, PCI Express technology, in a cost-effective manner, in a scalable manner, power efficient, fully backward compatible manner. And because of these attributes, PCI Express has evolved as the ubiquitous I/O across the entire compute continuum. Every type of computing system that you can think of, whether it is a PC, a handheld device, whether it is a workstation, whether it is a smartphone, whether it is a server, cloud, enterprise, HPC, embedded, IoT, AI, automotive, you name it, PCI Express is the backbone interconnect of choice. You have one stack, you have one silicon, but it is capable of working seamlessly across multiple form factors across this entire continuum. And we support different widths in addition to the different speeds that we talked about. We have speed widths that go from single lane, which is by 1, to 2 lanes by 2, by 4, by 8, by 16. And fundamental promise of full backward compatibility is that if you have a card that you purchased from way back when, 2 decades back, and which was during PCI 1.0, and you put it in a system today, which is PCI 5.0 based system, it will still interoperate. So we have multiple PCI Express devices that are leading these kind of technology transitions, speeds and feeds transitions. Those are things like networking, CPUs, GPUs, FPGAs, accelerators. These are some examples. PCI Express supports multiple protocols through its PHY called alternate protocols. And these are the ones, all of these are driving the tremendous need for speeds and feeds. And as a technology, we are moving forward with these evolutions that we have. Now, the tenet of an open slot with backward compatibility is to make sure that a part that you have designed by any member company, it continues to interoperate as long as the backwards compatibility is there. Now, that's a tall order to achieve, and yet we have done that very successfully. We have ensured a plug and play ecosystem with thousands of devices over these decades. And this is not a coincidence. It is a result of the methodical approach that we have taken and we have successfully deployed with appropriate enhancements since the beginning of this technology. Now, let's do the question and answer session. Let's get those rolling and let's have a dialogue on how PCI Express has managed to, but more importantly, how we are going to continue to be the primary interconnect of choice in the compute continuum. So, Mihaela, let's see what questions we have.
Yeah, thank you, Debendra. And so today we're celebrating the past, the present, and the future of the PCI Express technology. So I wanted to start with the simple question of why was the PCI Express specification created? What industry needs did it address?
Yeah, I always like to talk about how PCI Express is revolutionary for all the new things it's done and how it's evolutionary for kind of that backwards compatibility Debendra was talking about. You got to remember that this 20 years ago when PCI Express was being created, it was building on PCI. And PCI had already solved a lot of the problems of the sort of first generation IO buses. So things we take for granted today, like plug and play, bus mastering adapters, all those things had been solved by PCI. But as a parallel interconnect, it was really kind of running out of steam, if you will. It's so hard to make 64 bits of data on a parallel bus all come at the same time so you can strobe those in. So the industry was really looking for a way to get away from those parallel interfaces, get more flexibility on the bandwidth. Because again, PCI had 32 bits and 64 bits, right? Debendra just talked about all the link widths you can do in PCI Express and all the link speeds you can do. So those were kind of the revolutionary things that were pushing us to do something different than what we had done before.
Yeah, and I think that what we did with PCI Express really was to find the balance between the old and the new, where we maintained the software model that was developed for PCI, which is fundamentally a load store model, meaning that processor data movement is very natural. You don't need a host controller or something like that. And we maintained that going from some of the first generation IO buses through PCI as a second generation IO bus and then into PCI Express. At the same time, we built on some of the things that had been introduced like PCI, like, Richard mentioned the plug and play architecture that PCI really brought to the industry. And we maintained that so that existing software would work with PCI Express, but we also extended it. So for example, the configuration space for a device in PCI is only 256 bytes. In PCI Express, we made that 4 kilobytes. And this has enabled us to add a lot of new features, again, in a backwards compatible way, so that all existing software sees what it expects and what it's familiar with, but new software is able to take advantage of new features. And we did a similar thing with the form factors. So the initial PCI Express card form factor was designed to be physically very similar to the PCI form factor, which in turn was very similar to the ISA form factor. So in terms of the physical aspects of the chassis, you could easily move from one generation to another among those technologies. And so, it's really about finding that balance, right? Having found that balance and really sticking with the things that were essential in the past technologies, but then enabling them to move forward.
Yeah, you remember we had that mirrored connector, right? So you could have a PCI connector on one side and PCI Express on the other. So the same slot on a system board could plug in either one. And for a time, that was huge, right? People always get seduced by the revolutionary side, the cool new shiny things. But what really makes the success over time, and Devendra said this a few times, right, is it really is that backwards compatibility, that evolutionary aspect of things that makes it so successful.
And what is more even impressing on top of that is, like, as we go from PCIe 1.0 to all the way to 7.0, right? If we look at the CAME specification, the CAME connector has, of course, the internals have changed, but in terms of backwards or forwards compatibility, if you have a card designed based on CAME 6.0 specification, you will still be able to plug that card into a system or a chassis designed as per the PCIe 1.0 specification. And if you have a card designed as per PCIe 1.0 specification, the same card will plug into a chassis designed based on the latest CAME specification. So all this backwards compatibility is amazing that we have been able to maintain over last 2 decades.
All right. Thank you all. And to go in a little more depth, what key features were introduced in the PCI Express specification that are still a fundamental part of the technology today?
So, probably this is a question we can go on for the rest of the session here, but I'll try to keep it brief. Let me highlight a few. First thing was, as Richard was and Dave were mentioning, that with PCI Express, we moved from the bus-based interconnect to the serial point-to-point interconnect. It was full duplex. It was differential, right? So serial point-to-point, full duplex, differential interconnect, right? And then we talked about the multiple widths and then the multiple speeds that we deliver in order to provide for the scalability, right? So people deploy different widths or they deploy the different data rates depending on the need that they have. And this has effectively, these techniques have really helped us drive pin efficiency. It's extremely efficient when you compare with any of the other external interconnects that are out there. Very pin efficient in terms of the bandwidth per pin, also, power efficiency, all of those things go hand in hand. Some of the other things that we have introduced with PCI Express is, of course, it is fully packetized. Once it is a links-based thing, you want to do things in packets, well-defined packets. It's split transaction. What it means is that you send a read request, you're going to get a completion at a later point of time. So you don't have to sit around in the bus waiting for the response to come back. Credit-based flow control, that's important. So you know how many credits you have, so you don't have to effectively do like a reactive flow control kind of thing. So credit-based flow control. So these are some of the things that we introduced with PCI Express in order to be scalable going forward, right? And sustain for multiple generations. And also, most importantly, this also helps us drive a lot of efficiency in the link, right? And that in turn translates to better performance and better power efficiency. Other aspects that we've been very careful about is around the reliability, availability, and serviceability, RAS for short, right? Especially in the enterprise segment, in the cloud segment, these are important. They're also important, by the way, in the handheld segment too, right? It's not that they're not that, but more so in these other segments. And we have these levels of reliability built across the stack. Like, for example, the links at the link level, when you look at the bits, we protect our data with cyclic redundancy check, CRC. At the transaction level, we have this notion of hierarchical timeouts, things like, hey, I sent a transaction, it has been a while, I didn't get the response back, maybe it is lost, right? So I need to generate a transaction so that somebody upstream doesn't completely think that everything is broken, right? At the point of egress, you do the timeout. So it's the hierarchical timeout mechanism that we introduced in the PCI Express. Things like error containment, right? You contain the error wherever you detected it. You don't let it propagate. You have to sometimes poison the data, right? And they're all very advanced architectural concepts that got built into PCI Express. Things like hot plug, for example, right? I mean, somebody wants to remove a device and plug in another device. You support that hot plug again. It comes with all kinds of things like how does software know? How do you inform it, right? I mean, how do you ensure seamlessness? We have worked through all of that. The other thing is around, power management. We have a lot of advanced power management features. Software can control it. Hardware can control it. Hardware knows when things are happening. So it knows to modulate, for example, link width, link speed from, we have different power states. Another important aspect is quality of service, right? We have these different traffic classes, right? Some types of accesses will be slow. Some need maybe less bandwidth, but they're very time sensitive. So we comprehend all of that, and we have built all of those into the specification. These are some of the key attributes that I would say, these have really stood the test of time. And of course, we build on that. And some of the recent other things that we have been adding is security, for example, right? It's an ongoing journey, right? I mean, we always try to make the best possible interconnect that we can deliver.
Yeah, the other thing that we don't think about very much is switching, right? So when we moved from that bus architecture, you had one set of pins on the host bridge. It was easy to have 3, 4, 5 cards all in parallel. When we moved to PCI Express, we go to this point-to-point serial interconnect. One of the things I always thought was just the coolest was the whole idea of a PCI Express switch. So it looks to software like a classic PCI to PCI bridge. And yet, you take that one-to-many construct of a bus and turn it into a bunch of point-to-point one-to-ones through switching. So that let us keep the expandability of the PCI hierarchy and everything when we move to the serial interface. So, and lots of cool stuff people are doing with that now with, various other technologies, switching in PCI Express. I don't know if we talked about cabling and optics and all the stuff that we're doing kind of moving forward. So all enabled by that switching construct.
Thank you. So looking a little bit more at the present, with many changes in the compute landscape, what do you see as the secret behind PCIe technology's success so far?
One thing, and this is kind of building on a point that was made a couple of moments ago, right, is that we've really continued to evolve and very actively respond to industry needs. And a particular example there, I think, that really stands out is in the low power space where, you go back in time, and initially most folks were focused on just all out performance, right? And not really so much concerned about power. And there were people saying, oh, you'd never get PCI Express into a cell phone or a similarly, constrained kind of a device. And for a while, there was some real turmoil, right, in that. But what happened is we developed a feature called L1 substates that enables PCI Express to go to extremely low power levels when idle, and that satisfied the industry need. And pretty much all phones these days use PCI Express technology. So we've really seen that we're able to, again, in an incremental way, right, move from one end of the industry to the other, and really satisfy a very, very broad spectrum of use cases within the same, fundamental technology.
Yeah, and I think the fact that we have one base specification that supports multiple form factor specifications. For example, you could have a silicon designed to a specific revision of the base specification, and the same silicon will be able to support multiple form factors like CHEM, for example, or it could be M.2, U.2, copper link internal, copper link external. All these form factors, these are enabled by a CPU design or a silicon design rather, that is based on a single base specification. So of course there is a common set of requirements that is all like silicon that you have on both sides of the link. They are required to meet the base spec defined requirements. Then the base spec defines end-to-end channel budget. But whatever happens in the system, like on the form factor side, it is all these form factors have the flexibility to kind of define what connector they are using and how they are distributing the insertion loss budget between the card side and the system side and so on. But just the fact that it is still a same base specification that is making all these form factor specification possible, I think is also among other things that Dave mentioned, one of the key points here.
You know, we talked a lot about backwards compatibility physically. Just I can take an old card, plug it into a new system. I could take a new card, plug it into an old system. But as Manisha was saying, the way we write the specs is even backwards compatible. So if you design something in 2003 to the 1.0 or 1.1 spec, if you followed the 1.1 spec, you did everything right, that same device is actually compliant with the 6.0 spec and the 7.0 spec, right? So you don't have to say, oh, I have this old 1.1 device. You can actually say and bring it to our compliance workshop and pass all the tests. And that device will actually be able to pass compliance testing for 6.0. I mean, if you did something wrong, that may not be true. So not like everybody can, but at least theoretically, if you followed the 1.1 spec, you'll be totally fine and totally compliant with, I think as long as any of us hope to keep doing this.
And I think that backwards compatibility is always a great attribute of PCI Express as a technology. And, it's also a great sustainability story, right? You don't have to throw away things. If it is working, you can just upgrade some other parts, not upgrade everything else. And, by the way, I really like, Dave, your example of how we pivoted to the handheld segment. I also remember all that turmoil, right? Hey, your low power state is milliwatts, we need microwatts, and here we were, right? I mean, we came up with L1 substates. So thank you for guys for covering that. Now, I let me add some more color here on some other aspects around speeds and feeds, right? I did talk about 8B, 10B, and why we made the transition to 128B, 130B, right? We always look into these transitions as an opportunity because there is always the challenges of the data rate. The question is, what do we do with that, right? We always look at it and say, hey, are there things that we could do better when we are making a transition so that it sustains ourselves, right? So the recent example is PCI 6.0 with the flit mode. And as I briefly mentioned, at 64 gig, we had to go with PAM4 signaling in order to maintain the same channel reach. Now, the drawback of PAM4 is because you are sending 2 bits within a unit interval, or like roughly speaking, a clock cycle, you basically have 3 eyes in there. Your number of errors just grows manifold, okay, which is measured as a bit error rate. It like grows by 6-7 orders of magnitude. So of course, the good news is that if you get a breather in terms of your channel reach and all, you doubled your data rate, but then the bad news is you get a lot of errors, right? And not just a lot of errors, a lot of errors, right? Now, okay, so how do we get around errors? Well, we'll do forward error correction. It's called FEC, forward error correction, in order to offset the high bit error rate so that, you bring the error rate down to a reasonable level, and then we have replay that takes care of things. Now, the question is, what bit error rate do we target, right? Well, clearly the networking standards are done 10 to the power minus 4 bit error rate. And the easy question is, hey, why not just copy that? Why not copy the forward error correction? Life will be easy. There's one problem though. They have 100 nanosecond latency adder for the forward error correction. And how much do we really want for a lot of our load store applications? Latency adder close to 0, right? So there is a mismatch there. And this is where, we say, hey, let's innovate, right? So we said, okay, again, we did the analysis, 10 to the power minus 6 error rate. That's the sweet spot. We can do a very simple forward error correction, okay? Now with that, because we are doing forward error correction, we had variable sized packets. Now we went to FLIT. FLIT stands for flow control unit. So it's a 256 byte entity that we chose. So fixed amount, you protect with your error correction, you protect with a CRC, which is cyclic redundancy check, make low latency the motto, right? And we put restrictions saying, hey, you must respond within this much amount of time. You construct it very tightly, and what you get is really a win-win situation. What happened? The results are really spectacular, right? I mean, additional latency impact, less than a nanosecond. What about the bandwidth efficiency? Actually, we got more than 2x because we constructed things much better. So for example, the bandwidth that you got, real bandwidth with the PCIe 5.0 at 32 gig, in a lot of cases, you will get more than twice the bandwidth because we took advantage of some of the features of the FLIT and made the link much more efficient. And reliability went up significantly. Well, what about the trade-off, right? Was there a trade-off? Yes, there was a trade-off. We did suffer slight loss in the channel length from -4 to -6. We, roughly we estimate, it's about 2 inches, okay, on in terms of channel length. Now, turns out we still meet the platform reach even with that slight loss in the channel requirement. So that's not really an issue, and it's a good trade-off to make. The other thing to remember from what we have seen is that materials improve over time. With improved materials, you're going to get that channel loss, whatever you lost, you're going to get that back. Once you design something to a very high bit error rate, very high latency, you are not getting any of those back. You are basically losing those applications, those memory applications, those coherency, those latency sensitive applications, you are losing them forever. So, it was the right trade-off. So effectively, we always engineer things really well. We make very data-driven decisions, right? We always look at transitions. Transitions are always challenging. They are always, you need to navigate them carefully, but we always come up with a win-win situation. And again, this is where that 975 plus member company combined industry strength, that lets us really innovate. We are bold at innovating. We are not shy in innovating. We don't innovate unnecessarily, but we innovate whenever we need. And with that, we continue this journey, and that's basically what we have seen.
Yeah, I'd like how, I think, Dave, you said it, we worked hard. And I think that was the understatement of the hour, probably, on, especially as Debendra's talking about FLIT mode, right? I mean, Dave's been driving us through the protocol work group and championing that for the last umpteen years. There's probably nobody better qualified to talk about how hard that actually has been to make it work. But we do. And, another thing, Debendra, you kind of hinted at, but I think we should make like a trivia question. How many employees does PCI-SIG have? 0, none, right? This is all volunteers coming out of that 975 member companies, right? So, we
all have different days on
that call, right? That are listening to us go on. You're the ones doing the work. So if you're not doing the work, come help, because we could use the help.
Yeah. Yeah, and that's a great transition to this next question, Richard. So as a standard body, PCI-SIG has existed for many years. It has a large membership base. It's very active. What factors contributed to its success in the industry as a SIG?
Yeah, boy, I should have thought of that. I should have saved my comments on all our members, because it really is, right? It's the people that make that really come to be. But the backwards compatibility and the fact that that's really a focus, right? All that makes the spec successful, which makes the organization successful. But anybody can join, right? One of the other things is we've got member companies that are gigantic. We've got member companies that are, I joke and call it, 2 guys in a workstation, right? It can be a very small company. All of them come in, they contribute.
2 guys in a garage, Richard.
What's that?
Sorry. I thought you were going to say 2 guys in a garage. Keep going.
Sorry. It's the old 2 guys in a truck movers, right? So I think there's a similar equivalent, and but all that kind of comes together to make the organization. And then we have a compliance program. Manisha and I, she's on this corner of my screen, so I'm pointing over at her. But, Manisha and I drive the compliance work group. That really helps ensure all that backwards compatibility, right, Manisha?
Yeah, and I think SIG's compliance program is one of the kind of I think important things, and I think it's like one of the best compliance programs in the industry. So among multiple workshops that PCI-SIG conducts, like four, right, between two different geos, three happen in Americas and one in Asia Pacific. And these events, so these workshops are free for any PCI-SIG member to join. So if you have a product ready that you need to get kind of tested, you can come to these workshops and join for free. Of course, you need to register in advance. But among other things that get tested at these workshops, the tests are designed such that your implementation gets tested against kind of different layers of stacked implementation, whether it's an electrical layer. There are a few tests catered for specifically testing the electrical side, file logical, data link layer, or transaction layer. So there are different tests that are designed to test your implementation for these different layers of implementation. And I think other than that, one important aspect of compliance workshops is different companies who attend this workshop, they get to interoperate with each other, make sure they are able to talk to each other and form a working link, whether it's like at a maximum data rate supported by both sides, maximum link width supported by both sides. So I think that's an important factor. And at the end of all of this, member companies do get on PCI-SIG's integrators list that is published on PCI-SIG website. So you can go to SIG website, look at the integrators list, and there are different categories that are listed in here. So various products in different categories get tested, whether it's a motherboard, whether it's an endpoint implementation or retimer or switches. And not just the endpoints, you can even get like an individual component on SIG's integrators list, a specific silicon on the integrators list. So yeah, I think compliance program is kind of an important aspect, as Richard alluded to earlier.
Yeah, and as Manisha said, did you all catch that? It's free. We don't charge for them. Obviously, it costs you something to bring. It's your time and effort. But back to the two guys in the garage huddled around our workstation vendor, right? Like those two guys can bring their product and interoperate with the latest and greatest from all the big names, from all the other folks in a garage. All that interoperability happens at a workshop. And between the SIG and our member companies, there are literally millions of dollars of equipment sitting there so that you could test with. As Manisha said, we're focused on interoperability. We're not trying to validate your design. We're just looking for the key things that are interoperability predictors. But for a lot of small companies, especially, they may not have access to millions of dollars worth of test gear. So it's a great way for them to show up and do it.
And it can be two guys or two gals, but
yeah. Sorry, I'm old. Me guys, it's kind of generic, but
yeah. But I think the on a serious note, right? I mean, the other interesting thing that I have seen is the developers conference, things like this. Our outreach program of effectively training the broader community so that we all develop strong communities of PCI Express around the globe, right? And that's basically, I look at that as really the strength that sustains us through this journey.
Yeah, no, I like your comment on community, right? Because certainly there's the training aspect of it, right? I think that's what people look at and they see it like, oh, I'm going to come to the developers conference to hear about what's happening with PCI Express 7 or, what's going to be beyond that. Or, I want to listen to Dave explain to me how I can use this new flip mode thing and figure that out. But really it is, I mean, I find them really appealing. Even though I've seen all the material and I know what there's going to be said, it still is that meeting the other people, right? Meeting the other engineers from other companies, getting that whole sense of community. So I'm glad you mentioned that because it really is another really valuable aspect, I think, to the conference side of the developers conferences.
And on the conference side, I think another opportunity that these developers conference provide is not just the member track where members get to know what's happening on the various specification development, but member implementation. So various SIG members who have been working on PCIe implementations and have run into some issues. So they can come to these workshops, share their findings, what issues that they ran into and how they mitigated those issues. So they can share this with the entire community. And that is something that happens in the membership track of presentations where any SIG member can submit an abstract and consider presenting their findings.
Yeah, no, that's a great one too, right? I think it was last US Developers Conference. Of course, all of us on the screen were presenting various sessions, and there was one case where there was a member presentation on a hot new topic, and we were all like, "Where is everybody?" Oh, they're over in the member presentation. So, sometimes it's not us, the so-called experts, that are the real appeal, right? It's the people who've been down in the trenches doing the work. So, yeah.
Yeah. Well, thank you, everyone. I think so. We've spent time on the past. We've talked about what's going on now and kind of shifting to the future.
Where's my magic 8-ball? Darn it.
Yeah. How does PCI-SIG plan to address the needs of the data demanding applications like AI? I think we hear a lot about that right now. And how will the SIG balance the needs of these applications with the ones that don't require as much of a high speed and bandwidth as AI?
Yeah, I like to joke that we were doing AI before anybody knew to call it AI, right? And when you look at the needs of platforms that are doing, ML, AI type workloads, first of all, they span a very broad range from, relatively simple kinds of use cases, excuse me, going up through, some of the most demanding computing being done today. And in a way, the fact that PCI Express was just always there and always doing what was needed, I think it's almost like hiding in plain sight, right? A lot of the things that PCI Express fundamentally enabled in terms of the topologies that we support, having multiple ports coming off of the host, whether it's from the root complex or by means of switches, this is really what enables you to compose these kinds of systems, particularly for the higher end, more demanding kinds of workloads. And at the same time, because we have that scalability up and down, you're not paying the cost of the high performance if your needs are in the lower performance end of that spectrum. So we actually scale very well all the way across this spectrum. And, I think of it as kind of a democratizing technology, right? Because what we do is really to hit that, where to dial in your level of performance, your balanced against your power, balanced against your system cost. Wherever you're trying to land on that spectrum, PCI Express can adapt to suit that interconnect need. And this has been true from day one. We always plan for this sort of scaling, and there's really nothing that we see going forward that's going to change that, right? We've already talked about going to the next generation of PCI Express, and I don't see that that's going to end literally any time, right? It's just going to keep moving forward, both in terms of just the raw performance, but also in terms of the scalability, the ability to dial in just exactly what is needed for the application at hand, top to bottom.
So to lean in more into what's next. So with 128 gigabit transfers per second on the horizon, and what is contributing to the speed increase? We know AI is one, and what are other things? And then what considerations do we need to account for in future versions of the spec? Like what comes after 7 even?
So yeah, it should be obvious that we will not stop after PCI 7.0 at 128 giga transfers per second. The compute industry, it will not stop innovating, nor should it, nor would we. or should we stop innovating, right? So we'll continue to innovate. We will continue to be the primary interconnect, right? I always tell people that, hey, our name is Peripheral Component Interconnect. We started with very modest aspirations. We are now the central. We are, of course, in the periphery, but we are in the center of the computing heart, right? Computing universe, no matter whichever system you build. So our innovation engine will continue to churn great technological advancements as we have always done. We are a very strong organization. We talked about that. The ecosystem, it needs us to deliver, and we are the ecosystem. We will deliver, and I'm confident that together we will deliver, right? I mean, the question that you asked me, Hela, was, hey, what are the drivers for the speeds and feeds? Well, there is an insatiable demand for compute. We are in this, compute cycle, right? Virtuous cycle of computing. New applications demands new capabilities, and we make new innovations on the capabilities side, which in turn drives new applications. It's all whether it is the CPUs, whether it is the GPUs, whether it is the accelerators, whether it is the FPGAs, all of these are, whether it is networking, whether it is storage, whether it is memory, most importantly, right? I mean, all of these have huge demands, and especially with alternate protocols like CXL, which basically are running on PCI Express. Imagine this: we PCI Express, we are no longer just a consumer of the memory bandwidth. We will continue to be the consumer of the memory bandwidth, just like processors are consumers of the memory bandwidth. Your GPUs are consumers of the memory bandwidth because they're connected through PCI Express, just like your networking is a consumer of the memory bandwidth. But in addition to that, we are the producer of the memory bandwidth, and that is really what is at short supply in this AI world, right? If you look into it, we can get as much of memory bandwidth and memory capacity that we can, and what interface best suits pin efficiency, bandwidth per pin. It is PCI Express, undoubtedly, right? And so this is a precious, memory bandwidth and memory capacity. It's really what is at the bottleneck in the AI revolution. You asked that question, and there has always, AI is of course the new frontier, okay? But there has always been applications that demand exponential growth in compute capability, right? Today it is AI. Yesterday it was something else. Tomorrow it will be something else. These demands will be there. There will be some sets of applications that are happy with the 2x every 2 years kind of thing, and then there are a set that need 10x every year. Okay, both will coexist, and this is where in the context of AI, for example, model sizes are growing 10x per year, especially if you are looking at the training. So the compute, the memory bandwidth, memory capacity, interconnect bandwidth, all of those demands are growing. They're exploding. And of course, PCI Express is critical on the interconnect bandwidth aspect, and also critical in delivering the memory bandwidth and the memory capacity, especially with what we have done with respect to the speeds and feeds. So we touched on the speeds and feeds. That's clearly very important. There is this insatiable demand for bandwidth. Okay, and not only that, we need to deliver that in a power efficient manner, because we are not getting any extra power. The amount of power that data centers are getting, it's fixed, and that quite frankly is going to be bottlenecking us. And the good thing that we have is our interfaces are very power efficient. We talked about that. From a silicon area perspective, people are getting source line limited. If you look into the PCI Express area, very area efficient, right? Very latency efficient. Okay. So you want bits to be in flight less. So latency efficiency. That's all of these are going to count towards us delivering the capabilities that the compute infrastructure needs, not just in the past but also going forward. Richard briefly, I believe, talked about optical friendly PCI Express. This is going to be very critical, because that's going to, how do you move a lot of bandwidth across? We are developing optical friendly PCI Express. That's a good medium through which you can deliver in a very compact form factor a lot of bandwidth. The other thing that I'm really excited about is, from a protocol perspective, the notion of unordered I/O, or UIO for short, right? It enables fabric topology. Semantics are, again, memory reads, memory writes, which are IO coherent, very useful in a lot of these computing applications, including AI. It's a great foundation for scale-up networks. Okay, imagine you're unordered, which means that you can now go through the switches without any ordering constraints. It's lossless fabric. That's the huge plus for PCI Express. So out of order characteristics, you can do dynamic traffic management, you can do congestion management, you can do a lot of things. A lot of these things, these concepts are going to come through and help us propel to the next generation of compute capability that we will deliver.
Yeah, you know, it's interesting. I was thinking as Debender was talking about all this cool new stuff, right? And just like we talked about, the revolutionary side is what always catches people's attention. But you look at what drove PCI Express over the last 20 years, and I'm just thinking to myself, here we are, the 5, 6 of us talking to all y'all. We're all sitting in different places, right? 20 years ago, to do a webinar like this, we either would have all gotten together in the same room, or we would have, you know, at very least been in our corporate offices. I'm in my basement office. I don't know about the rest of y'all, but, you know, I have gigabit Ethernet out to the internet, right? 20 years ago, that wasn't even visible. So, you know, there's been so much in our world that has driven higher and higher bandwidth, things that we really take for granted. You know, storage, I spent a bunch of my life as a storage guy. Storage today is just magic compared to what it was 20 years ago.
Hey, by the way, the storage and Ethernet are connected through PCI Express.
Yeah. If it weren't for PCI Express, right? Yeah. And 20 years ago, if you'd have said, oh, we're going to have native PCI Express attached storage, we all would have laughed at you, right? The disks went round and round back then. You know, there wasn't any of this solid state storage. So, yeah, you know, drivers, kind of back to your original question, the drivers have really been a lot of kind of common stuff, right? Not flashy, but the things that we all take for granted in our lives.
Yeah, and I think one of the really key pieces here is people are always excited about revolutions, right? But you have to have a way to get there, right? Yeah. And this has always been one of the strengths of how we've approached developing PCI Express, focusing on the how do you get there from here angle, while you maintain that level of growth, right, that satisfies the industry's demands in terms of, you know, both the bandwidth capability, the power performance, the pin efficiency, right? All of these different things, they're all focus areas that have a very strong aspect of linearity to them, if you will, which actually enables the revolutions then, because you can count on it, right? This technology is there, it's going to do what's needed. And really, yeah, to your point, right? A lot of applications that 20 years ago seemed completely unsuitable actually have turned out to work very well. Essentially cutting out kind of the middle parts, right? And again, now this is a system level of efficiency where you don't need to convert from this to that to the other thing, because you can just hook it up directly on PCI Express.
Yeah, you used the term democratize, I think, Dave, earlier on, which I thought was a fantastic way to describe it. And part of that is not just that all these speeds exist, but we've all talked about the fact that you can negotiate, right? If I've got a really high speed component and Dave's got a really power efficient lower speed component, they still negotiate and talk to each other. And I don't think we touched on the dynamic side of it, right? As Debender was talking about AI, you know, there's all these things that are happening, and then there's dead time, right? One of the cool things about PCI Express is you could be running 128 gig with this new upcoming PCI Express 7.0, and those same two components can just negotiate down and say, hey, we're not very busy, let's drop to 16 gig or all the way down to 2.5 gig.
Or you can dynamically modulate your link width.
Yeah, and the width too, right?
Any real dead time, right? You can just go from 16 lanes to 1 lane and not miss a beat in terms of real traffic getting exchanged. So those are some of the things we have built in.
Excellent points. And one other question, I think both Debendra and Richard touched on it a little bit, but how do you see PCIe architecture coexisting with other standards that use PCIe technology?
We're good friends. And I mean, I say that sort of half jokingly, right? But it's true. The PCI-SIG, to build on Dave's democratize thing, right? Both are very open to people that want to come in. We're partnered with numerous other organizations, right? OCP on form factors, CXL, and other consortiums that have done protocols. Debender mentioned really early on that alternate protocol negotiation, right? We open our physical layer up to let anybody build on top of it. So places where PCI Express makes sense, we go after that, we innovate, we focus. Places that may not be our core competency or that don't necessarily make sense for our 975 members, we make it available so other people can do that.
And there's a real need, actually. If you look at a platform, for example, right? I mean, you're not going to have a separate set of pins that does, for example, my company does as do our competitors, symmetric multiprocessing cache coherency. We don't want to have a separate set of pins that does that. You want your pins to be fungible. And this is where we are at a great spot, to Richard's point, that, hey, the PHY is available. You can put a PCI stack, you can put the other stacks, and then decide, depending on the configuration, what do you want to run? And that basically results in a win-win for everybody.
And to add to few more examples, right, on this one, Mihela, like one example is U.2 form factor, right? The specification that we develop in PCI-SIG is based on SFF8639 connector that is defined in SNIA. Few more examples from PCI-SIG is the recent copper link internal cable, external cables that were defined in PCI-SIG are based on SFFTA 1016 and 1032 connectors respectively. So on these ones, we do collaborate very closely with SNIA to make sure that changes that we are incorporating, I mean, they are kind of mutually acceptable, and that we are kind of making sure keeping member implementation in mind and not breaking things for anybody. To add to few more examples on this one is EDSFF specification, right? To one of the earlier questions, I think you asked about one base specification that made multiple form factor specifications possible, right? And in addition to the ones that PCI-SIG kind of defines, like KMM.2, U.2, EDSFF specification is owned by SNIA. The connector is owned by SNIA. But again, it does refer to PCI-SIG's base specification and KM specification. So it is again required that the same silicon designed to a specific revision of specification is meeting KMM.2 and on top of that EDSFF specification as well. So that's one of the areas where we do have a good collaboration with SNIA. And to what Richard mentioned earlier, right, on the OCP side, we do have OCP NIC or DCMHS specifications that are part of OCP, and we do collaborate closely with OCP to make sure that we are kind of developing these specs in collaboration.
Thank you for that. We're close to at the end of the webinar, but I'll end it off with one last question. What will continue to make PCIe technology successful and valuable to the industry?
Everybody's probably sick of hearing us say backwards compatibility, but
Yeah, and I would say that we need to keep innovating, right? Just to reiterate again what we have been saying, the compute industry has been innovating. It will continue to innovate. It will continue to undergo significant changes. And we as PCI-SIG and as a developing PCI Express technology, we need to be nimble. And we need to stay focused on the key strength. And that's, again, that has been our strength, right? That we are nimble, we stay focused, we deliver things. We don't necessarily run after some shiny object somewhere, right? Saying, hey, we want to be there too, right? And, as I mentioned earlier, I see the demand for speeds and feeds to be insatiable. They have always been insatiable. They will continue to be insatiable. They will continue to challenge us, and again, we will continue to deliver, double the frequency, keep the latency flat as much as we can, right? And we have been fairly successful. Keep reducing that picojoule per bit, keep doing the low power things that, Richard and I touched on before, and, keep the silicon area under control, right? Because we have huge number of lane count, and keep as much as we can, keep the channel reach the same. We will, of course, be investing in alternate media like optical things that we talked about, but that's part of the journey, right? We need to be always open to what the possibilities are, and we need to think about what is in the best interests of our community here, right? And we need to make sure that, as you know, PCI Express, it's the central interconnect in all the computing systems. So we all together have a huge responsibility, and together we need to make sure that we look at the things in its totality, and we just need to go about solving it. The problems will keep getting more and more challenging with time, but again, we have proven that we can out innovate, and we can out innovate for any kind of a challenge that comes to us, and we will continue to do that, and we will continue to deliver for that whole ecosystem. We just need to keep doing things the way we have done. Be open, be inclusive, and but be very aggressive with respect to where we want to intercept our technologies going forward.
Yeah, and optical is a great example of that, Devendra, right? Because right now what we're doing is we're building optical options. I think everybody expects there's going to come a point in time where we're going to run out of speed on copper. Now, when PCI Express started, I didn't have gray hair, so it's been a while. And I actually remember when the electrical work group chairs told the board of directors, 5 gig, this might be it for copper. We might not be able to go any faster than 5 gig. And since then we did, as Devendra said, 8, 16, 32, 64. Now we're doing 128. So I don't know when that day is coming, but I may have no hair left at that point. So we'll see.
I had a full head of hair when I started. Now, losing that.
Get out of here.
But no, it has been a great journey. I think, we will, like I said, we'll continue to innovate, and we will be, we will be there, right, together. Right?
Maybe that gives us a
There's
good
just no other alternative. I just don't see it.
Yeah. Well, as Dave said, I don't think any of us intend to quit, but maybe that's a good call to the younger members of our audience. Yep. Get in here. We need your help. So come join the work groups, and you be the next generation. You tell us how PCI Express 12 is going to work. So.
Yep. So thank you all. I think we're at the end of the webinar for today. I hope you all enjoyed it, and I'm going to hand it back to Kevin for closing comments.
Great. So yeah, that is the last question we'll have time for today. Any questions we didn't get to today submitted will be answered offline. Also wanted to note a recording of today's discussion will be available soon on Bright Talk, as well as the PCI-SIG YouTube channel. So you can watch that on demand. Wanted to finally thank our panelists for their participation, and everyone out there online for joining us today. We hope you'll join us for future PCI-SIG webinars. Thank you.
Thank you. Bye.
Thank you.
Thank you.
Bye.